Episode 3. Episode 2 ended on a single instruction: classify by operation, not by content. This episode is that instruction applied to 4 of the most influential memory architectures in the field. We are not going to review 4 papers in turn. We are going to ask all 4 of them the same 3 questions, and then show that each system's answer to those questions already predicts how it will fail. By the end you should be able to look at a memory design you have never seen before and say, in one sentence, what it is structurally blind to. 4 systems, 3 questions, and 1 table at the end that I think is the most useful single artifact in this series so far. Here are the 4, drawn at the same level of detail and in one shared visual grammar. That last point is doing real work. Each of these systems is normally met through its own paper's diagram, and those 4 diagrams share no conventions at all: different boxes, different arrows, different words for the same thing. Redrawing them in one grammar is most of what makes this episode possible, because it lets you put them side by side and see that they disagree. MEMGPT treats memory as an operating system. Generative agents write everything and decide at read time. AMEM keeps notes that rewire themselves on insertion. HippoRag indexes the structure of a corpus, offline. 3 questions. What gets written, and who decides? A rule, a prompt, or the agent itself? How is it addressed, by what key, and what question does that key quietly assume you're going to ask? And when is it revised, on what trigger, at what granularity? These are not new, they are the write, index and update operations from episode 2, asked of a whole system instead of a single item. The 3rd question is the one that will do the most damage. Hold on to it. One warning about the 3rd question. It is the one people answer with a shrug in design reviews, and it is the one that decides whether your system is still correct in 6 months. 3 objectives. Read 4 influential architectures as 4 answers to the same 3 questions. Predict each design's dominant failure mode from its right path, not from its benchmark scores, from its right path, because the right path is visible before you run anything. And choose between them for a given workload from a cost table rather than from taste. That last one gets empirical support near the end of the episode, and the support is stronger than I expected when I planned this series. And a note on method: we read each design from its own description rather than from its evaluation, because a benchmark tells you how it did on somebody else's workload. MEMGPT frames the problem as an operating system. Main context is what sits in the prompt and is bounded. External context is archival and recall storage. And the agent does its own paging between the two, through a function call interface. The analogy earns 3 things: an explicit budget, an explicit moment at which something must be evicted, and an explicit interface the agent can see. What it does not earn is the idea that memory is a passive store. Paging moves bytes. It does not decide what is worth keeping, and that decision is the whole problem. That gap between moving bytes and choosing what to keep is where the next 3 architectures all try to live. The budget is fixed and the conversation is not, so this picture is inevitable. As main context fills, something has to leave, and the system signals that to the agent rather than silently truncating. The agent then chooses what leaves and what gets fetched back. Watch the item that gets paged out and never requested again. Nothing happens to it. It is not marked wrong, it is not consolidated, it is not deleted. It is simply out of view, indefinitely. Whether that is a feature or a slow leak depends entirely on whether anything ever revisits it, and in this design nothing does. Hold that thought, because a store full of items nobody revisits is the opening problem of episode 5. This is the part of MEMGPT that mattered most, and it is not the metaphor. Memory operations are named, typed, and exposed to the model as tools. Once an operation has a name, it can be logged, it can be priced, and eventually it can be learned, which is exactly what episode 4 is about. But notice the gap this opens. A tool that is available is not a tool that is used. The interface makes a good decision possible, it does not make the decision good. Every system in this episode inherits that gap, and only one line of work has tried to close it. That line of work is the whole of episode 4. So here is the right path, stated as a chain. An observation arrives. The agent notices that it matters. The agent calls a memory function. If any link in that chain fails to fire, nothing is written and nothing complains. The dominant failure is therefore silent omission. The store ends up holding what the agent thought to save, which is not the same set as what the task later needed. On the cost panel, this design is cheap to write and cheap to read, and there is nothing anywhere in it that prices whether a write was the right write. Remember that empty third column. It is the column that decides whether any of this is trustworthy. Generative agents make the opposite bet. Do not try to decide what is worth keeping. Keep all of it and decide later. Every observation becomes a time-stamped natural language record, appended to a stream from which nothing is removed. The stream is the ground truth. The effect of this choice is worth being precise about. It makes the right decision trivially reliable, because there is no decision, and it moves the entire difficulty of the system to read time. That is a legitimate engineering trade, and it is the cleanest example in this episode of a design whose failure mode you can predict from one sentence of its description. One sentence into the description, and you already know where it will hurt. Read time works like this. 3 terms, combined as a weighted sum, and I want to be exact here, because it is often written as a product and it is not one. Recency is exponential decay since the record was last accessed. Importance is an absolute rating the model assigns to the record itself, independent of any query. Relevance is embedding similarity to the current query. In the original implementation, all 3 weights are set to 1. Keep the shape of this in mind. Episode 6 shows a system from this year whose retrieval score also has exactly 3 terms, and all 3 of them are different ones. The shape is durable, the terms are not. Periodically the agent synthesizes higher-level beliefs from the stream, and those reflections are themselves stored, with pointers back to the records that produced them. Credit where it is due, keeping the pointers is more than most systems do. Now look at what is not on this slide. There is no arrow back down. Nothing ever reruns the inference when the stream changes. A reflection formed on 20 observations is not revisited when the 21st contradicts it, and it is never withdrawn. The evidence link exists, so the belief is traceable. It is simply never rechecked, which is a different property. That distinction between traceable and rechecked is the hinge of the second half of this series. The right path is the simplest of the 4, everything observed is appended, reflections are appended on top, and nothing is ever removed or revised. The dominant failure is a store of beliefs that are traceable but never rechecked, sitting in a corpus that only grows. Read cost climbs with the whole history rather than with the difficulty of the question. 2 later episodes pick this up directly. Episode 9 treats the unrevisited belief as the self-confirmation trap, which is the central problem of the second half of this series. Episode 5 treats what happens to all of this as it ages. Both of those episodes begin, in effect, from the arrow that is missing on the previous slide. AMEM changes what a write is. A write is not a string, it is a record with named fields, content, a timestamp, keywords, tags, a contextual description. Named fields matter because they let you query by field rather than only by similarity. The organizing idea is Zettelkasten, and it is taken as a design discipline rather than a metaphor. The value of a note collection is in its links, and the links are made at filing time rather than at reading time. Then the interesting move. Which existing notes a new note connects to is decided by the model, not by a rule. That single decision is what separates this design from a tagged vector store. Each insertion retrieves its nearest neighbors and then links to the ones the model judges related. So the graph is not built once and then queried, it is rewired on every write. Watch the cost as the clip runs. The work done per insertion is a function of the neighborhood, and the neighborhood grows, so the marginal cost of the 10,000 write is not the marginal cost of the 10th. And watch what is absent again, nothing in this loop ever checks whether a link was correct. The links are generated, stored, and then trusted for as long as the store exists. Generated, stored, and trusted, 3 verbs, and only the first 2 are cheap. And there is one more step, which is the most interesting thing in this architecture. When a new node arrives, the neighbors it just linked to can themselves be revised, their tags and their contextual descriptions updated in the light of what has just been filed. Look at what that is. It is an update operation that fires automatically, on a real trigger, at a meaningful granularity. It is the only one of its kind in this episode. It is also the only update path here that is paid for on every single write, and by the end of the next 5 minutes that will look like a bargain. The write path has 4 steps: construct the structured node, retrieve neighbors, generate links, revise the neighbors you linked to. The dominant failure follows from step 2, write cost grows with the size of the store, and link quality is never verified, so an early wrong link propagates quietly through everything filed after it. On the cost panel, notice that this is the first design in the episode with anything at all in the verification column. Be careful about what that means. What gets checked is structure. Does this note relate to that one? Not truth. Whether a structural check is worth its price is a question this series returns to every time the verification column is not empty. Hipporag indexes structure rather than episodes. A fixed corpus goes in. A model extracts entities and relations from it, offline. The result is a graph index, with additional edges joining terms the retriever considers synonymous. The neurobiological motivation here is not decoration, it does real work at read time, as the next slide shows. But look hard at that first box. The input is a corpus. It is not the agent's own experience. This is a retrieval architecture that the field routinely reads as a memory architecture, and the difference between those two things is what slide 19 is about. That conflation between retrieval and memory is probably the most common category error in the field right now. At read time the query's named entities become seed nodes in the graph. Relevance then spreads outward from those seeds, and passages are ranked by how much of it reaches them. The consequence is worth stating plainly, because it is the strongest single capability in this episode. A question that requires 3 hops of reasoning is answered in 1 retrieval step rather than 3 rounds of search and read. Nothing else in this episode does that. If your workload is a fixed corpus and genuinely multi-hop questions, this is the design, and the rest of this episode will not talk you out of it. The neurobiological framing earns its place precisely here, and nowhere else in the design. So let us be exact about the trade. What the graph index buys: multi-hop reachability in 1 step, structure that survives paraphrase because the edges join entities rather than strings, and a read cost that depends on the neighborhood rather than the corpus. What it gives up: there is no right path from the agent's own experience, so nothing the agent does ever enters the index. There is no update path below a full rebuild. And every extraction error is inherited permanently, with no way to ask which edges came from a weak extraction. On our 3 questions, question 2 is answered better here than anywhere else in this episode. Questions 1 and 3 are not answered at all. The right path runs once, offline, over a corpus, extract, link, index. The agent is not in that loop at all. The dominant failure is that the index inherits every extraction error, and its revision granularity is the entire index. There is no such thing as a small correction. On the cost panel, note that the write gauge is high but paid once rather than per observation, which is a genuinely different kind of cost from AMEMs. Read cost is the lowest of the 4. And the verification column is empty again, for the 3rd time out of 4. 4 systems in, and the verification column has been empty 3 times out of 4. That pattern is the reason this series exists. Here is the whole episode in 1 table. Read down the columns. What gets written, what the agent calls for, everything observed, a structured note, or a corpus prepared offline. How is it addressed, paging plus search, a score computed at read time, fields and tags and links, or propagation over a graph. 4 systems, 4 genuinely different answers, and none of them is a rephrasing of another. Now read the third row, and notice that it is the only row where the answers stop being interesting. When is it revised? When the agent says so, never, on every insertion, or on a rebuild. 3 of those 4 answers mean the same thing in practice, not reliably, and not at a useful granularity. And there is the finding. 3 of these 4 architectures have no principled update path. MEMGPT revises when the agent happens to choose to. Generative agents never revise, by design. HippoRag revises by rebuilding the whole index or not at all. Only AMEM has an automatic update path, and it pays for it on every single write. This is not a new observation, it is exactly what episode 2 found from the other direction, when the operation by decision maker table showed update and forget as the operations that stay unowned longest. 2 different routes, the same hole. That hole is why episodes 4 and 5 exist. 2 different routes to the same hole is stronger evidence than either route alone. There is now direct evidence on this. A study last year put 12 memory systems and 2 baselines on a common harness, across 5 classes of workload and 11 datasets, and found that no single architecture dominates. I want to separate 2 readings of that sentence. It is not a diplomatic result, the kind of thing people say to avoid picking a fight. It was measured. What it means practically is that the selection question is real, there is no default you can adopt and then stop thinking about. And it means a paper's headline number is telling you about that paper's workload, not about yours. Which is close to the most useful thing a benchmark paper can tell you. So, 3 concrete workloads. 1 long unbounded session, take MEMGPT style paging, because the binding constraint is the budget and that is the only design here that treats the budget as a first-class object. Many short sessions with 1 user, take AMEM style structured notes, because cross-session reuse needs fields and links, and at that volume you can afford the per write cost. A fixed corpus with genuinely hard multi-hop questions, take a graph index, because nothing else answers 3 hops in 1 retrieval and the corpus is not changing anyway. And generative agents is missing from that list, which needs explaining rather than glossing. It is the right answer when the record itself is the product, a simulation you intend to study. It is the wrong answer whenever read cost is bounded. Lab 3. Pick a single observation and trace it. Log its write, both the trigger that fired and the exact key it was stored under, because the key is the part everyone forgets to record. Then log every later retrieval that returned it, and every retrieval that arguably should have. Then ask the store a question that the key was never designed for, and write down what comes back. 30 lines or so, against the claims triage corpus in the repository. It pairs with Lab 2, Lab 2 asks who owns each operation, and Lab 3 asks what the addressing key quietly assumed you would want. Those 2 answers together are most of a memory design review. 5 takeaways. For architectures, 3 questions, for genuinely different answers, and not one of them a rephrasing of another. The right path predicts the dominant failure mode, and you can read the right path before running anything at all. 3 of the 4 have no principled update path, and the 4th pays for 1 on every write. No single architecture dominates across workloads, which makes selection a real question with a real answer. And the last one, which is the bridge, a memory operation that has a name can be logged, priced, and eventually learned. Next episode, the Learn Policy column, filled in. That last point is the bridge out of the organized segment of the spine and into control.